Okay, so gradients and directional derivatives. This should start to answer some of the questions I was getting early on when we first started talking about surfaces and what the derivative was going to mean in terms of surfaces. We're also going to be going back to some of our vector knowledge here. All right. All right. So first of all, last week we described the partials, right? Let's say fx, the partial of f with respect to x, as the slope in the direction of x, right? The slope of the tangent line in the direction of x. So we can look at the slope of a surface in any direction, and we use vectors to indicate the direction that we're looking. So let's start off with some definitions here. All right, so I'm going to read this and I'll put it up on the board just like I normally do. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector. All right, so if f is a differentiable function, oh, I forgot the I, is a differentiable function of x and y, then f has a directional derivative in the direction all right, I can't spell direction, hang on. In the direction of any unit vector. All right, now we're going to define our unit vector. We'll call our unit vector u, and we'll call it AB over here. All right, so the notation we use for directional derivative is a capital D, and then a subscript of the vector that we're using. So du fxy is the directional derivative in the direction of u of the function f, and it is going to equal fx xy times a plus fy xy times b. All right, now this should look familiar to you. Maybe it's just vaguely familiar, but notice here this, right, this right here is just fx fy dotted with AB. All right. So our directional derivative is really the dot product of two vectors, one formed by the first partials, the other formed by the unit vector that we're using to determine the direction. All right, now the unit vector is going to make some kind of angle with the x-axis. Remember, because we can slide vectors back to the origin. All right, so if the unit vector, right, so if u makes, make that a vector, right, if u makes an angle theta with the x-axis, all right, then I should say here with the positive x-axis. Actually, I'll do that. I just want to make sure that's clear with the positive x-axis. that keeps our angle positive, basically, is what I'm concerned about there. Okay, with the positive x-axis, then, right, then we can write u as cosine theta sine theta, because remember, u is a unit vector, so its magnitude is 1, so that works that way. All right, which means that the directional derivative du fxy is going to be fx cosine theta plus fy sine theta. Okay. Now this vector right here, fxy, is a particular vector. Okay, it's something that gets used all the time. All right, fx fy as a vector is called the gradient. Okay. Now the gradient, we have notation for the gradient. As far as that goes, there's a couple that we use. There's one that I pretty much always use. So you can write gradf for the gradient, or you could write an upside down delta f. All right, this is pronounced del f. All right, not delf, del f. All right, del f is that's the notation that's the notation I learned. That's the notation I've always used. So that's pretty much the notation I'm going to use going through the rest of this here. All right. Okay, so we can pull a definition out of this. I'll do that before I move the board up. All right, so we have a definition that says if f is a function of two variables, then the gradient vector, all right, so if f is a function of two variables, then the gradient vector of f, right, then del f of xy can be written as fx xy fy xy, or as partials, partial of f with respect to x I plus the partial of f with respect to y j. Okay. And del f, put it down here. Whoop. Del f is going to be, oh, I'm sorry, the directional derivative. All right, du of f is going to be del f dotted with u. Okay. Now we can use the directional derivative, and we can use the gradient rather, to find those rates of change, the way everyone wants to think of the derivative. All right, so the directional derivative gives us the rate of change of our surface at a particular point in all possible directions. All right, so the question that we usually want to answer here is, what is the direction of maximum change, right? Where is the function changing most rapidly? Where is it the steepest? All right. So to answer that question, all right, we have a theorem. And again, I'll read the theorem and I'll put it on the board. All right. So if f is a differentiable function of two variables, then the maximum value of the directional derivative is going to be the magnitude of the gradient, and it'll occur when u has the same direction as the gradient. All right, so the theorem that we're going to use here. All right, let's see if I can do this. All right, if f is a differentiable function of two variables, differentiable function of two variables, then the maximum rate of change, is, okay, so the maximum rate of change is given by the magnitude of the gradient and in the direction of u. All right. Where u is in the same direction as the gradient. Okay. All right, now this is also true for three variables. It's true for beyond just two variables. All right, it does scale up. All right, let's take a look at a function. All right, so I'm going to take the function f of x equals x e to the y. So f of xy, sorry, equals x e to the y. All right, so I want to find the maximum rate of change of f at, we'll say, point P. P is 2, 0 in the direction from P to Q, from P to Q, where Q is the point 1/2, 2. All right, so we are dredging up a whole lot of vector information that we haven't looked at in a number of weeks. Okay. First of all, we need the gradient. All right, so the gradient, that's not hard to calculate. That's just the first partials. Right, so I need the gradient of f, which is going to be fx, fy. All right, so fx, the derivative of this with respect to x, y is a constant, so the derivative of that is 1, so that is just e to the y. The derivative with respect to y, x is a constant, and the derivative of e to the y is e to the y, so that's just going to be x e to the y. All right, so there's my gradient. So now at the point 2, 0, all right, the gradient of f is going to be Let's see, if I put 0 in here for y, I'm going to get 1. And if I put 2 in for x and 0 in for y, I'm going to get 2. All right, so there is my gradient vector. Now I need to get my directional vector. All right, so my directional vector, that's my u. I have to start out with the vector pq. All right, because we're going from p to q, so we're going that way. All right, so dig up out of your brains how to do that, right? We do q minus p, coordinate by coordinate. All right, so I'll write it down just because we haven't done it for so long. All right, so q minus p, q minus p. So this ends up being negative 3/2, comma 2. All right, now we need to calculate the unit vector. All right, so remember the unit vector, where can I put a note? Let's put a note over here, right? The unit vector for, let's say I have a vector v, is v over the magnitude of v. All right, this is how we do a unit vector. So that means I need to calculate the magnitude of PQ, which is going to be the square root of 3/2, negative 3/2 squared plus 2 squared. Where did I write that? Which, when I work that out, ends up being the square root of 25 over 4. So that ends up being 5/2. All right, so I guess I'll write this over here just so you have it as a formula, right? So the magnitude of v is the square root x squared plus y squared. All right, so all these little formulas you got to go back and remember now. All right, so now to get u, I'm going to do PQ over the magnitude of PQ. All right, so that is going to be, this in the denominator would make that 2/5 times negative 3/2, 2. All right, so where am I? 3. Right, okay, I see where I'm going. All right. All right, so to get rid of those, we get negative 3/5. No, negative 3, yeah, negative 3/5. And then 4/5. Okay, I need some more space here. All right, so I need the directional derivative, right? So the directional derivative, du, and we're going to do this in the at the point. So that's going to be f of 2, 0. All right, so that's going to be 1, 2, dotted with this negative 3/5, 4/5. All right, so remember how to do the dot product, right? Multiply the coordinates and add. So 1 times negative 3/5 plus 2 times 4/5. So this is going to be negative 3/5 plus 8/5, which is going to be 5/5, so that's going to be 1. All right, so there is my directional derivative at that point. All right, so now let's look at the maximum rate of change. All right, so the max rate of change right, where is the graph the steepest, is in the direction of the gradient. right, so it's in the direction of the gradient. So that's going to be del f of 2, 0. And we figured out that was 1, 2. All right, so there's the direction. And then the magnitude and the actual rate of change. All right, so the actual rate of change is going to be the magnitude of the gradient at that point. There we go. There we go. Okay, so that is going to be the magnitude of 1, 2, which is going to be the square root of 1 squared plus 2 squared, which is going to be the square root of 5. Okay, so we end up with the maximum rate of change of my function, x e to the y, is the square root of 5, and it occurs in the direction of 1, 2. All right, so if you were to graph this using GeoGebra, you could locate that point and you could see where the function is the steepest. The gradient, right, at the point P will always be perpendicular to the level curve through P. All right, so that's another thing to look at there. All right.